Okay, so let me continue with the next algorithm that we want to talk about, which is boosting. Okay, boosting is used to build a strong classifier using a set of sometimes extremely weak classifiers. Okay, each one of those small classifiers can be accuracy of a little bit better than random guess. This is a cool thing about boosting. So you use, for example, the 100 classifiers. Each one of them has the accuracy of like 55%, a little bit better than 50-50, a little bit better than random guess. But by combining a lot of them in an iterative method, we will achieve very accurate results. Boosting. Okay, boosting tries to build a strong classifier using a set of weak classifiers in an iterative method, an adaptive method that changes the distribution of your training data over time by focusing more on previously misclassified data samples. Okay. So this is an iterative method and this is an adaptive method. It keeps working on the data based on the past results. So if your previous classifiers make bad predictions, then we change the distribution of training data. We change the training data that we provide to next classifiers, so that it can take care of the problematic samples. So that's why it is not a static. It's not like, for example, bagging, that we train 5 different classifiers simultaneously and then make the final decision. To train each base learner, to train each classifier, we check the results of previous classifiers in boosting. So instead of sampling randomly and constructing several classifiers independently, in boosting methods, we try to construct a sequence of predictive models such that new models focus more on the data samples that were problematic for previous classifiers or previous predictors. So this is the idea. So I will show you some pictures to understand the structure of the system, this method. To make sure that a learner will focus more on problematic samples, in each iteration we will give extra weights to the samples that misclassified in previous rounds. In each iteration, we change the distribution of training data samples so that records that are wrongly classified will have their weights increased in next iteration. And the records that are classified correctly will have their weights decreased in next iteration. Okay, so let me show you this picture. In the following example, suppose that 5 and 7. So this is our first classifier. Suppose that 5 and 7 are hard to be classified correctly. So the first classifier made a mistake for 5 and 7. So these are 5 and 7. By the way, this is the index of the data sample. So these 2 data samples misclassified by this classifier. So we increase the weight of them in next training set. So if this is the first training set, this will be the next training set. So I add another 5. So in round 2, the second classifier, remember this was the classifier 1, this is classifier 2, not the same classifier, the second classifier. We will provide it with more 5s so that it can learn 5 better. Again, 5 and 7 are difficult samples. It misclassifies them, so we increase them. So this is the third classifier. Okay, this is classifier 3. This is what we provide as a training data, as the training data to classifier 3. So look, a lot of 5s and 7s. I still make mistake, I still make misclassification for 5 and 7. This will be what we provide to classifier 4. A lot of 5s and 7s. Okay, so this will be the training data. Remember, this will be the training data for round 4 or classifier 4. So as you see, this training data set, it has a lot of 5s and 7s, so that finally this classifier can learn how to detect them, how to correctly classify them. So this is the approach. So this was only the first part of boosting. Okay, the second part will be a weighted voting. Okay, so we have 4 classifiers that are trained now, but we don't just combine the results by a simple voting. We do weighted voting based on their performance. So the classifiers that did better in prediction, we give them better weights to make the final decision. So in combining a step, after training a sequence of base learners using the above adaptive training set, the algorithm uses a weighted voting system to make the final decision. In other words, each base learner has a vote, but better base learner gets a larger weight in voting. So there are 2 main techniques that we use in boosting. First of all, we use adaptive and iterative techniques to modify our training data set over time to focus more on to detect and focus more on problematic samples for next rounds of classifiers. And secondly, we use a smart weighted voting technique to give more weights to the vote of better classifiers. So this is the idea. In summary, boosting includes 2 main steps: base learner training in an iterative and adaptive fashion by focusing more on previously misclassified data samples in each iteration, and second, combining the prediction results of the base learners based on weighted voting system to make the final decision. So this picture, it is one single picture that provides a lot of information. So these are 4 rounds of the boosting method. So boosting in a picture. There are four different classifiers, 4 rounds of this boosting method. And these are our training data sets. So look at this is our training data set. Okay. So suppose that these are the training data set includes, for example, 4 different types of samples. Okay. This is our first round. It means that this is our first classifier. We train this classifier using this data. As you see, the data set is even. And this is the prediction results for the first classifier. Okay, so the first classifier correctly classified these data samples, correctly classified these data samples, but misclassified these samples and these samples. This is first round, first classifier. So in next round, in round 2, we change the distribution of training data set based on these results. So this first group that classified correctly, we reduce the weight of that for the second classifier. Same thing for this guy. And these two groups that misclassified by the first classifier, we increase the size of them. Okay, so for example, we increase the weight of them or repeat those samples in the training stage, so that my second classifier learns better how to detect these two, and it works, right? So as you see, this is second classifier and these are the results. It now correctly classified these two, but now it misclassifies this fourth group. So fourth group, it was correctly classified in last round by the first classifier, but now because we reduced its weight, the second classifier didn't learn it well, so it misclassified it. So now in the third round, again, we increase the weight or number of those misclassified samples. So again, we increase back this. The first group, this group, it classified correctly twice. So in the third one, we reduced again more of those samples. So the third classifier in third round, it didn't learn this first group very well. That is why it misclassified, but it classified these two correctly. Okay, and we keep doing that. We were lucky that the fourth classifiers could classify all of the samples correctly. It does not necessarily happen always. And even our last classifiers misclassified some of the samples. Usually this is the case, but in this example, just for the sake of visualizing how boosting works, the last classifiers classifies everything correctly. But as you see, it really achieves the main purpose of ensemble learning, which is diversity. So as you see the results, you see that the prediction results are very different. Okay, the samples that one of them classified correctly, the other one didn't, and it was completely adaptive. So by time, we focused more on problematic samples. So these samples were problematic for first classifier. That is why we increased the size of those samples so the second one could learn it. Okay, and so on. So all of these things was the first step one of this boosting method, and after that, this is time for step 2, which is voting. Okay, so and voting, as you see, is weighted based on the detection results. So this guy, look at this, its accuracy, it gets less weight, low weight for the voting. But this guy, the performance of this sample, this second classifier was better, so we give more weights for its classification in final decision making. And the last one had the best performance, so we give more weights to the last one. But again, this is voting, right? So we combine the results of all of those classifiers using voting technique, but give more weights to better classifiers. Remember, it is not necessarily true that the last classifier is the best one. Remember that. So this is just an example, but maybe the last classifier can be even the worst one. But it can detect the samples that was problematic for previous round. This is important. And final decision based on voting. I really like this picture. This is from Max Welling from UCI. This single picture alone represent or visualize or illustrates the structure of boosting. So if I plot the accuracy versus round, okay, so this is your accuracy, versus number of iterations. Okay, usually it is like this. Okay, all right, so more iterations, let me call it cost or error. Let me call it error. Okay, so the error goes down when you increase the iteration, the number of iterations, or training more and more. But at some degree, you see that, for example, after here, it's almost constant, so it doesn't change anything. Okay, so if we plot this curve, you know that, okay, this is time to stop, because after that it doesn't help anymore. So this is time, maybe the best time to stop. Sometimes you will see something like a curve like this, which is also very common when you see something like that. It means that at this point the results is getting worse by training more. It means that at this point overfitting happened. Even for boosting, overfitting happened. So we can again stop at this point. Let's continue. This is the pseudocode for AdaBoost. Did I talk about AdaBoost yet? Yeah. So look, there are several different implementations of boosting available. AdaBoost stands for adaptive boosting. Some people call it AdaBoost, but it stands for adaptive boosting. And gradient boosting, and a very good example of that is XGBoost. They are the most popular techniques, and they usually provide very accurate results. Recently, they have been very popular especially in Kaggle community. This is a pseudocode for AdaBoost. They are different implementations, but the main idea is the same thing for all of them. So you can review the pseudocode later. I'm not gonna ask you to implement AdaBoost, but I will teach you how to use, for example, Python libraries to use AdaBoost and XGBoost and so on for your problem. Okay, because the best implementations of that are already available in those libraries. This is another example. So this was the original examples by the inventor of boosting method in an article called A Tutorial on Boosting by Robert Shapier. So this was the person who invented this technique. And this is a simple picture and shows you how it works. So suppose that we have a data set here to classify. It has two samples, positive samples and negative samples that can represent anything. So positive, for example, if tomorrow is rainy or sunny. So the question is tomorrow rainy? So your answer is positive or negative. Or the question can be, this patient has cancer? The answer can be positive or negative. Or the question can be, is a stock market going up tomorrow? Your answer can be positive or negative. Doesn't matter what application. But this is a binary classifier, and we want to apply boosting on that. So at the beginning, as you see, positive samples and negative samples, they have equal weights. Okay. This is our first classifier that I use. I want to train my first classifier, and this is just a line. Okay, it is just a simple linear model, the simplest type of classifier ever. The art of ensemble learning, especially boosting, is that it lets us develop the most accurate machine learning models using the combination of the simplest classifiers. Okay, so we start with a line, only a simple line. This is our first classifier trained on this data set, and as you see, this is the prediction. So this model misclassified these three samples. So these three samples misclassified by the first classifier. So we increase the weight of them. So these three have more weights now, and for next round. And now I use this data set. And by the way, these samples, for example, that correctly classified, as you see, they have less weights now. So by weight, for example, in training a step, you can add more of those samples that misclassified and less of those samples that correctly classified for next classifier, so that your next classifier can learn better those samples that misclassified in previous round. So look, let me repeat that. So these three samples misclassified by this classifier, right? This is a classifier. It predicts everything on the left hand side as positive, everything on right hand side as negative. So this classifier misclassified these three samples. Okay, so we can understand that probably these three samples are difficult samples that was problematic for first classifier. So for next round, I increase the weight of them, or I repeat those samples in next round. So this is a new training data set that will be used for training the next classifier. Okay. So now this is the second classifier. This is my second classifier that I'm training that using this new training set. So in fact, I changed the training set in each round. Again, a very simple classifier. Now, because I increased the weight of these samples, I added or repeated those samples, it could learn those samples very well, but it misclassified now three other samples. That's okay. Now I again change my training data by increasing the weight of these three misclassified samples. Okay, and reduce the weight of, for example, this sample was the samples that I classified that correctly second times. So I really reduced the weight of that. This is my new training data that I provide to the third classifier. So this is my third classifier. Now, this is how the third classifier is trained. I just changed the training data. So the process is very simple. I just change the training data in each round and provide this new training data again to a new classifier. I just changed the distribution of my training data. And now this is the third classifier, classifier 3. This is what happened, because the weight of these samples and these samples were pretty high. It learned to classify them correctly and now misclassified these samples. Okay, so now I have three classifiers that each one of them learned to make correct prediction for some of the samples that were problematic for previous rounds. But the samples, like this sample, for example, the samples that were classified correctly in previous two rounds, we are not worried about them in this round anymore, because we will eventually take votes. So I had these three classifiers. First round, classifier 1, classifier 2, classifier 3, and then I give them some weights. Okay, some weights based on their accuracy. The better one gets the higher weight, and then the combination of them will be something like that. Okay, the combination of these three classifiers will be this. okay, which is a perfect classifier in this example with 100% accuracy, right? So I built, look at this, there are 3 lines. By combining them, I get something like that. So by by training 3 poor classifiers, I could build a great classifier, only using 3 of them. So in practice, you can use 100 rounds or whatever. There's no limit on that. Again, you can always plot this graph, your error versus the number of iteration, and iteration or rounds of training, and usually your graph is something like that. It means that after this point we have to stop because it's almost get constant. Sometimes you see a graph like this. Again, if you see something like that, this is time to stop, because after this point overfitting happens and your accuracy will be worse. And this is by the way, this is a common strategy for every machine learning. So every machine learning model, you can train it more and more and more and more, or make it more complex. So this can be also complexity. You can make your machine learning model more complex, or training more and more. You can do it for every machine learning model, and this technique tells you where to stop. All right, how can boosting improve the accuracy? It increases the variance. So as you remember, bagging reduces the variance, okay? But this is the other way. It increases the variance. So when you have, for example, this is your data and I want to do regression, so I use a lot of very simple, very simple regressor models. For example, this line, and then another one, this line, and then another one, this line, maybe this line, this line, this line. So very simple models, okay? But if I combine them using like boosting technique, this will be the combination of them, okay? And same thing for here in classification. So this is my first classifier, this is my second classifier, this is my third classifier, and so on. And after voting, the combination of them will be, for boosting, will be something like that, which is ideal. Okay, so if you remember, in bagging I had very high variance models. I use voting to make a good one, but in this one it's the other way. I have very poor, maybe high bias models. I combine them to get a good result. So these are different types of ensemble learning that we can always use to get great results. Now, when a model is too sensitive to the data, or in other words, when a model is overfit, we call it high variance. It means that the variance of the outputs with respect to input is too high. The model is too sensitive. So for regression, for example, look at this. That maybe give you good results on training data, only on training data, but this is a very high variance model, okay? It is overfit. We call it high variance. It means that the model is too sensitive. It changes a lot. The fluctuation of this prediction, the fluctuation of the output is too high, okay? So this is a bad model. In bagging, we use a lot of these models using like voting technique or averaging technique. So for example, this is one of them. Okay, this is the other one. So look, the thing is that they think differently. They are not all the same. This is the idea. Both of them are high variance models. Both of them are too sensitive. Both of them have a high fluctuation for the output, but they are different. They are high variance in different ways. So by voting or averaging, for in this case by averaging, the average of these two will be a curve, like, let me use another color. Okay, so after voting, this will be the average of these two, which is an ideal model. So I had two high variance. I had two high variance overfit model, and using bagging technique, I made a good model, something like that. So this is bagging, okay? But for boosting, this is the other way. I want to build a good model using several models that are very low variance. So there are some models that are very much underfit. So look at this is, for example, one of my model. Okay, this is another model. This is another model. Okay, so I have some models that I high bias, this time we call it high bias or maybe low variance. Okay, so they are underfit. They are too simple, in other words. But using the boosting technique and working on maybe the technique that we used for improving each one of them based on the data of misclassified data of previous rounds, and also after voting or averaging, the combination of these three lines will be something like, maybe something like that. Okay, which is again a good model. So those three were high bias, low variance, but this new model, which is the combination of those three, is an ideal model for our case. All right, so random forest is a great algorithm. I talked a lot about this last semester, and I'm not gonna again talk about all details. I put the slides here, but this is optional because I completely covered that in 4661. But remember that random forest is a great algorithm, and you should know how it works, and I highly recommend you to use it in your project. Okay, so the idea of random forest is to make a group of decision trees rather than a big tree, a group of decision trees as diverse as possible, as different as possible, and make the final decision based on a combination of them rather than one decision tree. It is specifically designed for decision tree because a decision tree is a good model, but it is very prone to overfitting. When we have too many features, for example, your tree will be easily too large and too deep, and then it goes to overfitting situation, and it provides bad results for future data samples. Using random forest, we use different data sets and also different features. So not only we use different data sets using like bagging, like what we did for bagging, bootstrap sampling. We use different data sets to train different trees, but also we use different features to train each tree, because we want to make sure, we want to completely make sure that the trees are as diverse as possible. So you can use it. Of course, I highly recommend to use random forest for your project. And the only thing that I want you to know in this class is that random forest is an algorithm that reduces the variance and solve the problem of overfitting. So the idea was to not only use bootstrapping to create different data sets, to train different trees that are as different as possible, but also in each tree split, in creating each node of this tree or decision tree, when we want to split based on features, we only provide a limited number of features to the tree to use. And this makes the trees very different from each other. So for example, if we have 100 features, okay, when we want to make the one of those splits, we always select the best features. You remember from decision tree, we always select the best features and put it on the top of the tree. But this time, I only provide 10 randomly selected features out of those 100, and I only provide these 10 features to my model. So rather than selecting the best of 100, it just selects the best of these 10. So by doing that, we will create trees that are very different from each other. Each one of them alone is not ideal, but we achieved the goal of diversity. This is important. So there is an example here. So we covered that in 4661, but I just want to show you this example. So for the Titanic problem that we talked about before, suppose that we have 3 features: age, gender, and passenger class. We want to create our decision tree, and we look for the best feature always. So if we just use a decision tree classifier, it always select the best feature of these 3, which is, for example, let's say age, and always put it on the top of the tree. So no matter how many trees I train, if I train 10 different trees, always the age is the best one. So all of those trees will put age on top of the tree. So the structure of those trees will be the same. But this is what I'm gonna do in random forest. In random forest, I limit the number of features that I provide to each tree. So, for example, at this node, let's limit our feature subset to only gender and passenger class, and ask the decision tree to select the best among these 2. So in this case, gender is the best one, so I put it at the top, and we do the same thing for the rest of the tree. So this is how we trained the first tree, and this is what's gonna happen. For second tree, I provide 2 other features to my tree and ask it to select the best of them. Passenger class is the best of these 2. I put it here on top and build the rest of the tree. So now, as you see, I have 2 trees that are completely different from each other. So look, the structure of them are completely different. So this was a very novel idea. It was a very cool idea to make sure that our trees are as different as possible. And in this example, what is the prediction for a passenger who is adult, female, and has second class ticket? So by the left tree, this one, let's check this one first. Second class, so I come here and female and adult, so not survived according to this tree. But according to this tree, it was female second class, survived. Okay, so as you see, there are two trees that make different predictions for this sample, but that is totally okay, because if I have many of these different trees and make the final decision based on combination of them, like voting for example, it turns out that it provides the best results. So these are the main three techniques that we covered: bagging, boosting, and random forest.